These are your 8-3 notes, and this is our introduction to graphing reciprocal functions. A reciprocal function is a form of a rational expression or equation. And so this is just an intro. Lots of patterns, lots of symmetry, and a lot of the same patterns that you've seen throughout the year with A, H, and K. So a reciprocal function is of the form where you have a 1 on top or maybe a number on top, but no variables on top, just a constant on top, so a 1 or a -2 or a 3. And then on the bottom is your formula. And the bottom is the variable. And so up to this point, we really haven't been able to graph these things. We never had the variable in the denominator. And so now we're going to look at what does that do? What happens when we actually put x in the denominator? Well, it does some crazy things to our graph. So they're basically saying that this portion is going to be a linear function. So if you were to graph just that portion, it would graph as a line. So for instance, you could have a 2 instead of a 1. That's just going to change some things. And when you have your function, you could have it over x. And so when you look at that portion, y equals x would graph as a line. You could have a -3, and then maybe x plus 5. Well, this portion, y equals x plus 5, would graph as a line. So if that's the characteristics of this, then we know that it's a reciprocal function. And it just can't equal 0 because you can't have 0 in the denominator. So I'm just going to fill in this table here. This is what they look like. This is the parent function. And so we're going to base everything off of the parent. The parent function is when you have a positive 1 over 1x, a positive 1x. Very simple form of the equation. You can't really get any simpler than that. And so it forms these two curves. Now, when you have these two symmetrical curves back to back, they're called a hyperbola. That type of graph is a hyperbola, and kind of looks like a parabola, but slightly different. A parabola continues to go outward forever, never, never in one direction. A hyperbola goes in both directions, and it approaches an asymptote. So we use asymptotes when we graph hyperbolas. And we talked about asymptotes before. It's a line that a graph approaches but never reaches. And so all non-zero real numbers are the domain and range. So as long as it doesn't equal 0. But if you notice, where this graph is approaching and is really undefined is the x-axis and the y-axis. So where one graph starts, the other one picks up. So if you look at this arrow here, it's approaching, but it'll never reach that. That's because the x-axis is an asymptote. And same thing, this upward arrow is approaching, but never reaches the y-axis. And so we have to, once we get to that point, we kind of skip over the x-axis and y-axis, and it jumps to the other side. So that's how that hyperbola is formed. Part of the graph is on to the left of the y-axis and underneath the x-axis. And then we define what happens on the other side. Now, sometimes they look like this. This is the parent. It's a positive. It's sort of going in upward. It's rising to the right. If you think of a positive line rising to the right, it starts down low and it's rising upward. That's a characteristic of the parent. So this is the parent function of reciprocal functions. The asymptotes, like I just said, are the lines x equals 0 and y equals 0, the x and y axis. The intercepts, where does it cross the x-axis? It doesn't, because it's undefined there. That number doesn't exist. If you look at when x would be 0, when x is 0, that would give us an undefined term because your variable would be 0 in the denominator. And it's not touching the y-axis because that's your asymptote. And so it's not defined. Where are we not defined? When x equals 0. If you were to plug 0 in for x in this equation, you would be undefined because you're not allowed to divide by 0. So I don't know if I feel like I put asymptotes on another slide, so I'm just going to define it here one more time. It's a line that a graph approaches but never crosses. And when I say never, I'm actually talking about vertical asymptotes. So of the vertical choice, every once in a while, they will cross a horizontal asymptote. So never is kind of used lightly there. Most of the time, they don't cross. So we use them to help us graph. So now we have the transformations. So based off of the parent, since it was all centered sort of around the origin and the x and the y-axis, we have these transformations that occur just like every other function we have studied. So look at the a value on top. The a value throughout the year has decided the stretching and the compressing of the graph, if it's steeper, if it's wider, if it's shorter or taller. It also determines the orientation of the graph. So if A is positive, it's opening up. If it's negative, it's opening down. So those same characteristics are going to follow with the reciprocal functions. H and K, same thing as before. It has a minus H, so it looks like the opposite of what it really is. And then the plus K is our vertical. So H is horizontal, and K is our vertical transformation. If H units right, if H is positive. So if H is positive, though, it's going to look like something like x minus 8. My board is not cooperating. And so that would be 8 units right. And so what shifts 8 unit right is the entire graph, which means your asymptote will also shift 8 units to the right. If you look at the H value and it's negative, it's actually going to look like a positive, because when you plug in a negative, it turns into a positive. So this would be 8 units to the left. And so the vertical asymptote is now at that H value. So x equals 8 is the equation of a vertical line 8 units to the right. For the K value, again, we are true to our sign. So if it says positive K, we're going to move up that many units. Negative K is going to move down that many units. And our horizontal asymptote now will actually be the K value, y equals K. So if we had an equation 2 over x plus 3, we're going to go up 3 units. 2 over x minus 3 would be down 3 units. And y would equal 3 or y would equal negative 3, depending on which one we're talking about. And that's a horizontal line. So it shifts the asymptotes. And the asymptotes are great once you understand them, because they sort of give us some boundaries. So they're really going to help us graph. Once you understand asymptotes, you really don't have to make a huge table of values to graph, because we know we're approaching those lines. The A value is basically just the reflection. So if A is less than 0, it's going to be reflected over the x-axis. So I just want you to draw a little quick sketch down here. Okay, so if we have a positive A value, positive A is going to rise to the right. And a negative A value would fall to the right. So it's going to start in the second quadrant and go to the fourth. Also, A decides how close we are to our asymptotes. Okay, and so we can maybe color coordinate if you want to use a highlighter or of some sort. I'm just going to use different colors. So if we have the parent function is, positive A, so this is just your parent. So this would be like y is equal to 1 over x. If A is greater than 1, we'll go further away from the origin. And so that would just give us a graph that looks like this. And so it's stretched vertically. It's stretching outward. It's pulling away from the origin. And so that would be of the form like y equals 3 over x. And then the other is when the A value is between 0 and 1, not really looking at negatives, but between 0 and 1, like a half or a third. It's going to still be in that quadrant, but it's going to actually be closer to the origin. And so that would be of the form y is equal to like 0.5 over x. So it's going to compress vertically. Okay? So lots of the same things that we've done before. So we're going to graph 2, and then we'll go from there. So we're going to state the domain and range after we're done. And so looking at this negative here can actually be absorbed with this 1. So that's my A value. So my A value is negative. So a negative A tells me we're going to reflect. The A value equal to 1, or the absolute value is equal to 1. And so that means that we're just going to be the same width as the parent. We don't have to worry about any compressing or anything, or compressing or stretching. The H value in this case is a -1 because of the x plus 1. That's actually H is equal to -1. So my horizontal asymptote is going to be of the form, I'm sorry, my vertical asymptote is x equals -1. That's going to shift us to the left 1. And so this is my vertical asymptote. X equals -1. My K value is equal to a +3. And so that means my horizontal asymptote is going to shift up 3 units. So this is my horizontal asymptote. We just call it HA. And this is my VA for vertical asymptote. And so if I go up 3 units, and that now serves as my new origin. So now I kind of define 4 new spaces where we could be defined. Since it's negative, we're actually going to be in the new 2nd quadrant and the new 4th quadrant, so to speak. So we're going to have our graph somewhere up in here and down in here. If it was a positive A, we'd have it in the opposite too. So now I just pick a couple points to help me figure out where is this located. So you can use a graphing calculator for these points, but maybe the easiest way is just plugging in values. Now when I plug in values, I want to make sure that I plug in values to the left of -1. So I can't use -1 because if I plug in -1, I'll get 0 in the denominator. So I'm going to start with like maybe -2. So when I make a table of values, I really don't need a lot because I'm going to use my asymptotes. So I just kind of need to know, where does this graph start? How close to those asymptotes are we? So I'm not going to plug in -1. I'm going to start with -2. And so when I plug in -2 into this function, I get -1 over -2 plus 1 plus 3. And a -2 plus 1 in the denominator gives me -1. So I have a -1 divided by -1 plus 3. -1 divided by -1 is 1, plus 3 gives me 4. Again, you can use your graphing calculator for that. So -2 is up at 4. That really tells me how close I am to those asymptotes without going into the nearest half. So that's the first order pair that I could use. I don't really need much more than that. From here on out, I know I'm going to be approaching my asymptote. So I'm going to try to draw the line and slowly approach. And I'm also approaching this green line without crossing. So really just a sketch. The other side of this graph is for values greater than -1. So we're going to skip over -1, and now I'm going to plug in 0. So when I plug in 0, when I use the equation, I'll get -1 over 1, because 1 plus 0 is 1, plus 3. So that's -1 plus 3, I get 2. So 0, 2 is the beginning point on the other side of my hyperbola. So now that I have that point, I'm going to approach the green line from underneath, and I'm going to approach from the right. And there is your reciprocal function. So when we look at the domain and range, if I move to the left and to the right, the only number that is skipped on the x-axis is -1. So for domain, what we're going to say is that x cannot equal -1, because when you plug in a -1, you get an undefined term. And for my range, every value is applied if I move up and down the graph, except for that that horizontal asymptote. So y is not allowed to be 3. And there you have it. So if the y value is 3, some things don't work out. So that's what they're saying here. We can talk more about that later. Let's try another one. So in this case, my a value is negative again. So if a is, it's a -a, we're going to reflect. So that tells me we're going to be moving downward. My absolute value of the a value is 4. So we're going to have a vertically stretched graph. it's going to be further away from my asymptotes. And then the h and k values. My h value is equal to 2, and so that's going to shift us to the right 2, which means my vertical is x equals 2. So if everything from the parent is going to be shifted to the right 2, I've got a vertical asymptote at x equals 2. That's my VA. My horizontal asymptote is -1. My k value is -1. That means I'm going to move down 1 unit from right where the parent is, so that would be y equals -1 for the horizontal asymptote. There's my horizontal asymptote. Again, we're going to be working with those new like second and fourth quadrants. So think of where those two asymptotes cross as kind of like your origin. Now we just got to figure out how far away we are from that origin. So this is where that 4 comes into play. So I'm going to go ahead and graph. I need to pick values less than 2. So I'm going to use 1. I'm going to start off with 1. So when x is 1, I plug it in. You can use your calculator. When I make this a 1, 1 minus 2 is -1 over -4 minus 1. A -4 divided by a negative is +4, minus 1 is 3. So 1 gives me 3, and that's all I need. And from there, I know I'm approaching up, and I'm falling down. If you wanted to plug in more points, or you can look at your table of values using the graphing calculator, you're fine. For the other side, I can't plug in 2, but I can plug in values greater than 2. So let's start with 3. If I plug in 3, I get a -4 over 1, which is -4 minus 1 gives me -5. So 3 gives me -5. And that tells me where we're at this way. So you can see we're a little bit further away from that intersection of the two asymptotes. And that is the vertical stretch that we're talking about there. Domain and range is already kind of stated for you. The domain, x cannot equal 2, and your range, y, cannot equal -1. Those are the only numbers that are not on the graph. They're not defined on the graph. So what I'd like you to do, I want you to give me the horizontal and vertical asymptotes of the parent function. So that's the equations. It's a vertical and a horizontal line. And then I want you to just sketch the graph of the function and to be sure to include those dotted lines to help you out. Good luck.